So I'd like to start out by talking about my favorite outage that's happened at Netflix since I've been here. So to understand the story, you first need to know that there's this one service that suffers from this problem that we call cold start. Basically, when the service comes up, it's not yet ready to take production traffic. Some code paths need to be executed. Otherwise, it's just too slow. And so one of the ways it's warmed up is that it runs tests. So the service comes up, a series of tests execute against it, and then it's ready to receive production traffic. So one day, an engineer adds a new test because there's a new code path. Now, what you need to understand is there's actually two different types of tests. There are unit tests, which can run right away, and then there are functional tests, which need some initialization code to run first before they can actually run. And so what happens is the service comes up, it runs the unit tests, runs the initialization code, runs the functional tests, then it's ready to take traffic. The difference between a unit test and a functional test is this annotation. Now, in this particular case, the engineer forgot to put the annotation that specified that it was a functional test, which means it ended up being treated as a unit test. And so the service came up, that test ran as a unit test, it threw this class not found exception, and then our users saw this, the Netflix streaming error screen. This is what happens when you click play and you're not actually able to watch a video. So just to recap what happened here, right? This was code that was correct and a test that was correct. And because the unit test ran, we had an outage, right? So I think like the lesson here is very clear. Unit tests are dangerous. Maybe we should focus more on, manual testing. No, of course not. So the real moral of this story is that complex systems exhibit unexpected behavior, right? So I'm here today to talk about failure. In particular, I'm here to talk about system failure, which we typically call outages, right, in our field, or a little bit more generally, we talk about incidents. So there's three parts to this talk today. The first is what I call the how, and that's examples of how we run into trouble even though we're actually trying to do the right thing. The second part is the why, and that is why it is that system failure is going to be inevitable, no matter what we do. And finally, I'll talk a little bit about what we can do about it to make things like a little bit better. Okay. So for the first part of the talk is called Antics. You'll see why in just a couple of minutes. Now that phrase I had up on the screen before, complex systems exhibit unexpected behavior, that's a quote from John Gall. Gall was a pediatrician who wrote a book in the 1970s that was called at the time System Antics, where he talked about complex systems. Now, he did not have, software systems in mind, but it's sort of shocking how many of his observations about the strange behaviors of complex systems really apply to the kind of stuff that we do. And he formulated what he called the Generalized Uncertainty Principle, which, to say it sort of succinctly, is that systems display antics, right? Systems are going to behave in weird, pathological, unexpected ways that you wouldn't be able to predict. Let's talk about error handling. So one observation Gall made is that most of the time, any complex system is going to have to be dealing with failures or errors, right? And we know this, right? We know that there are transient errors that we have to deal with all the time. Our error rates are not zero in our services, right? Disks go bad, God knows what's happening inside the network. And just to bring this home, there was this really great paper out of the University of Toronto a few years ago where they looked at a bunch of different open source projects that are often used in distributed systems. Things like Cassandra and Redis and some of the Hadoop projects. And they looked at failures that were reported in the field, right? So someone is operating this service, something bad happens and they submit a ticket in and it actually was some bug in the code. And there's a lot of really interesting results from this paper, but the one that's my favorite that is most relevant to this talk is that, so in almost all the cases where there's a catastrophic failure, and by catastrophic failure here, the authors mean that either there was like a widespread outage that was caused, or there was persistent data loss. In almost every single case, one of the contributing factors was that there was some like transient, like non-critical error that happened, but there was a bug in the error handling code. Right, so like the exception handling block had a problem. It like swallowed it or didn't catch it or whatever, and that contributed to making things worse. So we can't get away from error handling. We've got to be able to do it. The problem is, as Gall points out, what gives us sort of grief and heartache is not that the problems we're trying to solve. It's that as we try to solve them, the coping mechanisms that we add introduce like new problems that are weird and difficult. So one of the ways that we deal with errors in our industry is with retries, right? So you make a call against an instance and it's bad for some reason, and then you retry. We do this at Netflix all the time. But consider the following scenario. So you have some kind of microservice architecture, and one of your services starts to have a problem, right? It becomes latent for some reason. Maybe it's like operating right near a tipping point. And so what happens when it becomes latent is that some of the clients start to time out, right? And what happens next? Well, the clients are going to retry. And more clients retrying is going to add load to that service. So what's going to happen? The service is going to go further underwater, latency is going to increase, and then more clients are going to retry, right? And what do we call this? It's a retry storm, right? This like pattern of failure is so common that we have a name in our industry for it, and it's a failure mode that happens because we've added error handling. So just two really interesting papers on this general topic of getting into trouble with error handling, both out of Microsoft and both out of the HotOS conference. One of them is about gray failure, which is where your clients, your customers, your users see a problem with their system, but your internal monitoring system does not detect it, right? So people see a problem, but you can't see it. The flip side of that is this other paper, which is where your monitoring system sees a problem, you have some automatic remediation problem, and that makes things worse, right? And that paper has case studies from Amazon and Google and Azure and Facebook. Let's talk about support systems. Or another way to put this is, why does Netflix need so many engineers? So I was at a conference a couple of years ago, and I was sitting next to a guy who had worked in the telecom industry for many years. And he asked me, how many people work at Netflix? How many engineers are there? And today, I don't know the exact number, but it's over 1,000. And he was kind of shocked at that number. And he was like, well, why do you need so many engineers to stream video, right? It doesn't seem like that hard a problem. And the reason is that we need so many engineers for this is because of what Gall calls the operational fallacy. And the operational fallacy is this idea that what your system spends most of its time doing is not what the system actually says it's spending most of its time doing. To take an example from outside of tech, if you look at Harvard, you might think that Harvard is a university, an academic institution. But actually what it is this enormous hedge fund that has this sort of like academic thing that's attached to it that they use to bring in additional funding and to maintain tax-exempt status. Similarly, there's this quote I really like from Adrian Cockcroft, who was an architect at Netflix, who's now at Amazon, where he says, Netflix is a monitoring company that is an interesting and unexpected byproduct also streams movies. Let's talk about another incident that happened at Netflix. So we had some non-critical service in our architecture that failed. In this case, it happened to be related to A/B testing. Right, so we can handle that. If the A/B testing system goes down, we can still stream video just fine. But what happened was that there was a critical service calling that was logging the errors, right? Every time it called out to this one, there was an error, wrote to the log. And now on that particular service, those log messages get sent out to Kafka. And the thread that sends those messages to Kafka takes a lock. And that lock was shared by the application threads. Right? And so what happened was that thread that was sending all those messages to Kafka was starving the application threads of CPU because of lock contention. And so the service throttled, and we had an incident, right? We couldn't stream. So, just to summarize what happened there, our logging system took down production, right? Logging is a support system. We don't need it to stream video, but we have it there because it's supposed to make it easier to operate our service. Let's talk about mitigation, right? So to pick on someone other than Netflix for a second, last year AWS had an S3 outage, and I saw a couple of nodding heads, and if you looked at the published root cause analysis, which was really interesting, one of the things that happened was that there's some internal billing process related to S3 that was slow, and they needed to debug it, and so there was an engineer who had to take some of the servers out of production in order to debug this issue. And in the process of trying to take these servers out of production, the engineer typed some command incorrectly, right? And the result was that they had an incident. So I've been developing this sort of conjecture over time about how complex systems fail. And my theory is this, that once systems get large enough and reliable enough, what you're going to see is that most of the incidents are going to happen either because some support system you have behaves in some weird, unexpected way, or because there's some non-critical incidents that's happening, and some operator has to go touch the system to mitigate it, and then the act of touching it contributes to having a critical incident. So to recap this, first part of the talk, so we have to do these things to improve availability, right? The things I've been talking about, like error handling, support systems, mitigation, we need those. They all improve availability or reliability, but they also all introduce their own failure modes, which are sort of more complicated and weird to understand than the original ones that we were trying to fix. All right, let's talk about drift. So it's very tempting for us when an incident happens to identify what the broken part was. Like, what was the thing that went wrong that led to our system failing, right? Like, what was the code change that had a bug in it that got pushed out to production? What was the configuration setting that was incorrect? What was the invalid data that somehow made it through our consistency check and got in and caused a problem? And, we sort of bang this drum of blamelessness because our instinct is always to attribute the problem to sloppiness, right? Somebody was not careful enough. They were not diligent enough in making some kind of production change. And if we could only be more careful in the future, we wouldn't have as many outages as we do today. So, there's this fellow named Sidney Dekker, who I imagine many people in the room have heard of already, who's a safety systems researcher, who has sort of an alternate view on thinking about how complex systems fail. So he says that sort of broken part model is not really useful in helping to build more reliable systems in the future. Telling people to be more careful is just not going to really help us that much. And he has a theory that he calls drift into failure. And what I'm going to talk about today is 4 aspects of that theory that I think are very relevant to the kinds of work we do, building and operating the kinds of services that we do. So the first aspect of the theory is what he calls unruly technology. And I think it's a pretty easy case to make that software is a kind of unruly technology. And the reason is that it's just really hard for us as human beings to reason about the behavior of software, right? We're just not good at that as people. And in particular, not only are we not good at reasoning about how software behaves, but we aren't really able to build models about how our systems behave at large scale, right? We just aren't able to do it. There's this quote I really like from Peter Alvaro, who's a professor at University of California, Santa Cruz, and is actually one of these rare professors that will talk at industry conferences, so if you ever have a chance to go hear him talk, I really recommend it. He has this phrase that fault tolerance isn't composable, right? You can't understand the fault-tolerant properties of a system by looking at the individual parts and saying this part is fault-tolerant, this part is fault-tolerant, and then I put them together and the whole thing is. And this is sort of an echo of Gall. So what John Gall said something similar, which was that you can't look at how a system is put together and from that information figure out how it's going to break. So just to really drive home how absolutely hopeless it is in being able to model complex systems, there was this really great paper out of the University of Washington last year where they were looking at 3 sort of relatively small distributed systems that had been formally verified, that researchers had built a formal specification that described the behavior of the system. They implemented in code, proved the code matched the spec, and they still found errors in all 3 of these projects. So these are like replicated state machines and distributed key value stores. And what was really fascinating is where the errors were. So it turns out that if you want to do like an end-to-end formal verification of a distributed system, you need to have some model of some of the system calls made by the operating system, because you're going to be communicating over the network, so you need to model that, and you're going to be talking to disk. And, modern operating systems don't have formal specifications. There's no formal spec for, the Linux system calls. And so what researchers have to do is they have to write what they call the shim layer, which is a model of those low-level primitives. And it turns out that almost all the bugs are there in the shim layer. right? Not in the application stuff that they were building. But because they made errors in the shim layer implementation, their code wasn't correct. And so, this sort of drives home that interfaces are really dangerous, right? But we know that. We know interfaces are dangerous. That's why we don't rely only, solely on unit testing. All right. Second part of the theory is what Dekker calls scarcity and competition. So this is the idea that we are always going to be resource constrained in our work, right? And in particular, we're always constrained by time, right? We don't have arbitrary amounts of time to validate things that we're doing, right? We're under schedule pressure, right? We need to deliver features which are the things that have business value. And so ultimately what that means is that we are always going to have to make trade-offs. In particular, we're always going to have to trade off between efficiency, doing as much work as we can in a given period of time, and thoroughness, right? Being as diligent as we can on any one particular task. And the safety researcher Eric Hollnagel calls this the Edo principle, the efficiency, thoroughness, trade-off principle. And once you sort of think about it as a principle, you will see it everywhere, right? Like, do I spend that extra half an hour reviewing this PR to really understand what this code change is? Or do I just, say it looks good enough and then I go to the next PR that I have to review? So this quote, remember, up here on the board, that was written by a pediatrician in the 1970s who was not thinking about software, right? This is not specific to software engineering. This is sort of endemic to the human condition. The third part of the theory is what Dekker calls decrementalism, which is a way of saying that systems do not go from being safe to being unsafe, but rather that there are sort of slow changes. It happens in small steps over time. And one way to understand this is to think about this scenario. When is it okay to push new code to production? At Netflix, we make a lot of use of canary deployments, right? So when we deploy new code, we deploy it to only a small number of instances, and then we monitor the behavior of the instances in the new code, and we compare metrics with the baseline, the code that was originally deployed. We have a canary analysis system that does like statistical analysis to look to see if the error rates are roughly the same, and the latencies, and whatever metrics you want to set up on there. And so you might say, okay, we're only going to push if the canary passes. Now, one day, canary failed. And the engineers looked at the code change, and they said, you know what? There's no way that particular change that triggered this deploy could have caused the problem. And so, we've had transient problems before. We're just going to push the code out to production. And so, this slide here, this is actually super unfair to those engineers. But I really love that tweet. The reason this is unfair is so there was a bug, the canary caught the bug, the canary failed. But that bug was in the baseline too. The bug was in the original deployment. It had been a latent bug that had been there for months. And because of a change in traffic patterns, it only manifested in the canary. So the change they were looking at was innocuous. But you could ask, well, in hindsight, why didn't they dig into why that canary failed and find the bug that was in the code? But you can imagine how you get to this point, right? You can imagine starting out doing canary deployments, and you say, okay, I'm only going to push my code all the way out to production when my canary passes. But then one day your canary fails, and you look at the metrics, and you're like, it looks like it could be a transient thing. It's really on the edge of the statistical tests. Let's just run the canary again, and if it passes the second time, we'll be good. And so you run the canary again, and it passes, and you push it out, and everything is fine, right? And so then sort of that becomes your standard, right? If my canary fails once, I'll run it a second time. So then another time your canary fails. So you do this for a while, and then your canary fails again, and you look, and you're like, well, it takes like 4 hours for us to run these canaries. We really want to get the code out. We're just going to look at that change, and if we'll make a reasonable judgment based on which metrics varied, and what the change was. And an engineer will decide whether or not it's worth, running it again, or, investigating or pushing it out. And so, you look, you make a judgment call, you push it out, and it's fine. That code was actually, perfectly fine. There was no bugs. And so that becomes your standard. And so this idea that your standard can sort of loosen up over time, slowly, is what Diane Vaughan called normalization of deviance, right? So Vaughan is a sociologist who studied decision-making at NASA in the wake of the Challenger explosion in the 80s, right? And so this was the phenomenon that she observed, how, deviations from the initial protocol sort of became accepted as normal. The last part that I'm going to talk about of Dekker's theory is what he calls sensitive dependence on initial conditions. Another way of putting that is what some people call path dependence. This is the idea that history matters, that history affects how your system behaves today. So one of the observations that Gall made is that if you encounter a complex system in the wild, it's almost never sort of created from whole cloth that way, right? Complex systems that work, that are successful, are pretty much always evolved over time from simpler systems that people added to. Right? And this has definitely been my personal experience. Any large complex system that I've dealt with evolved from a smaller system. And one of the consequences of that is that you're going to make decisions earlier on in the life cycle of your projects that are completely rational based on the local information you have, that are going to have sort of far-reaching impacts later on that are going to bite other people, including possibly future you. So to take another example from Netflix, we've got this service called EVcache. It's basically an in-memory key-value data store. It's very similar to Memcache or Redis. We use it to front things like Cassandra clusters and other services. And so one of the call paths that EVcache is in this example here. There's a playback service which calls a URL service which calls into EVcache. Now, the playback service is actually resilient to the URL service going down. The URL service is not a critical service. If URLs goes down, like it just like times out or it just fails, the playback service has some fallback logic that it can execute. So, one day, there was a spike in traffic. And the result of the traffic spike was that the network interface cards on all the EVcache instances saturated, right? And so when that happens, the calls from the URL service to EVcache started to time out. Now, the EVcache client in the URL service was configured such that if it couldn't hit the EVcache cluster, if there's a timeout, it would treat that as a miss. So instead of saying, I couldn't call it, there's an error, it says, oh, the data's not here. The cache is empty. The playback service could handle the URL service erroring, right? If that thing went down, like it was on fire or late, it could handle that. But it could not handle the case where the URL service said, the data's not there. And so we had an outage. So it turns out that it's a configuration option. It's not that EVcache is hard-coded to do that, but it was configured in this case to treat errors as cache misses. And not only was it configured that way, but that was the default configuration. And so you might ask, well, why was it default configured to do that weird behavior? And it turns out that historically, that was the right thing to do. In most use cases, that was the correct behavior that you would get. And so that's what the EVcache client team did. They set the configuration by default to return a miss. But that team didn't know that. They didn't have that information. So just to recap the drift part of this talk. So all the things I've talked about here, right? The nature of software, how people behave when they're resource constrained, how people can only make decisions based on local information, how projects, persist over time, and historical decisions that happen earlier on affect things later. Like, this is all baked in, right? None of this stuff is going to change anytime in the next, 100 years or so. Like, software is software and people are people. So, the final part of this talk, I'm going to talk a little bit more optimistically. So, there are some things we can do. We can't fix everything, but we can make it a little bit better. And so I'll talk a little about Chaos Monkey. So Chaos Monkey is a service that we have at Netflix that randomly terminates instances that are running in our production environment. So I happen to be the author of the current implementation of Chaos Monkey, but I'm not the original author of it. It's a little bit hard to show the behavior of a system like this, but one thing I can do is show you a picture of our dashboard that shows the termination rate. And you can see we're terminating, about between 5 and 10 instances a minute between 9 o'clock and 3 o'clock. So it only runs during business hours. And you'll notice that somewhere around like 2:40 p.m., it stops for a little bit and then comes back. And that's because Chaos Monkey has terminated itself. So Chaos Monkey is not opted out. It's not, it doesn't, and so it stops. It doesn't kill itself for killings for a while. Then it comes back. And the motivation for Chaos Monkey is that we wanted, at Netflix, our engineers to build services that were resilient to instance termination, right? When we migrated from data centers to the cloud's a noisier environment. But we don't have a way at Netflix to enforce process on people, to force them to build their stuff in a certain way. But we can provide incentives. And Chaos Monkey is a form of incentive, right? It brings the pain forward of building a service that's not resilient. And so, if you have to constantly deal with the fact that your service is going down because you built a stateful service when it could have been stateless, or you only have one instance in your cluster when there could have been many, or your client doesn't have retries, the more that you feel that pain, the more motivated you're going to be to actually address that problem. And so that's what Chaos Monkey does. It sort of makes the wrong thing to do harder. More recently, in the past couple of years, we've been sort of trying to generalize the ideas behind Chaos Monkey, and these ideas have come to be known as chaos engineering. And the idea behind chaos engineering is that, well, we can't really build theoretical models of how our system is going to behave, but we can use an empirical approach. We can study how our production system behaves by doing experiments on the system. Now, our particular application for doing experiments is to identify vulnerabilities at Netflix. So we do experiments on our production system because we want to find problems that could be outages one day and eliminate them before they actually become outages. And we do these experiments in the production environment directly. And the reason we do our experiments in the production environment is because of what scientists call external validity, right? If we only do experiments in the test environment, then we don't have a lot of confidence that those results are going to generalize to the production environment, right? I mean, the traffic patterns are totally different. All different kinds of code is deployed in there. The config is different, right? And so the only way we can have maximal confidence that our results are generalizable, that they actually apply to production, is to actually do the experiments right in production. So the risk that we're trying to mitigate with our chaos experiments is these days is that we're trying to identify vulnerabilities to failures of non-critical services. So by that I mean we have a ton of microservices at Netflix, but not all of our microservices are critical to users being able to stream video, right? A lot of them sort of add some value, but if they go down, it shouldn't take the entire site down. For example, there's a service that remembers where you were when you were last watching a movie, right? A bookmark service. If that service goes down, when you bring up Netflix, it should just start you at the beginning, right? It would be like a really crappy experience if you just had like an error message if that service went down. So we have to be resilient to those sorts of non-critical services failing. And we have this tool that we built called ChAP, which is our chaos automation platform, which is we've been able to use to automate running these experiments. And to explain ChAP, I'll run through an example. So if we take that earlier failure I talked about before, where the EVcache cluster got saturated, if we'd been able to, if we had run the right experiment, it would have been, are we vulnerable to EVcache going latent? So we would like to run an experiment that says, if the EVcache cluster goes latent, what happens? And so the way ChAP does this is, if you set up this kind of experiment, the first thing it'll do is it'll clone the URLs cluster and form two smaller clusters, a control cluster and an experiment cluster. Then it'll route a fraction of production traffic that would normally go to the URL service to those control and experiment clusters. So those are, binary copies of the URL service. It's writing the same code. And we're not doing shadow traffic here, right? We're actually rerouting that traffic. So that's real production traffic that's going to those two clusters. Then what we do is ChAP uses our failure injection to inject failures from all the traffic that lands on the experiment cluster that's calling out to EVcache. It'll inject latency in there. And finally, we'll use our automated canary analysis tools to see if there's any difference in the behavior between the control and experiment clusters to see whether we're resilient. So there's a website called principlesofchaos.org which describes more generally how it is you can set up chaos experiments for your own environments. I'm going to briefly just go over the different principles. The first principle is whenever you're going to run an experiment, you need some kind of hypothesis. And the hypothesis for chaos experiments is typically about the behavior of your system. So you need to have some idea of how your system normally behaves. And when you're going to run an experiment, you want to know what do you think the deviation is going to be from that steady state normal behavior when you're running that experiment. Now at Netflix, one of the KPIs we use in all of our experiments is this metric called SPS, or stream starts per second. This is a count of how many times a Netflix customer is able to hit play and successfully able to stream a video. And you can see it actually has a nice sort of diurnal pattern. And we're pretty fortunate at Netflix that our traffic patterns are pretty predictable, generally speaking. The second thing you want to do in any experiment is you want to inject some treatment into it, right? You want to inject some kind of real-world event, which is the kind of thing you want to check that you're resilient to. Now, these days, what we do mostly is we're either injecting failure, so we'll fail an RPC call between services, or we'll add latency to an RPC call between services. And that actually is a good way to model many different kinds of failures, right? So like if one service, starts using up too much CPU, or it starts, garbage collecting because it's using too much memory, in both cases you can sort of model that as additional latency. The third one is you want to run your experiments in the production environment, as I mentioned earlier. So what we do is we route fractions of production traffic to these experimental clusters that we're running. Fourth one is that you want to automate your experiments, because an experiment that you ran 6 months ago may not apply anymore, right? All our systems are undergoing constant change. If you just do this like once a year, 3 months out, the results may not hold anymore. And so we have ChAP, integrated with our deployment pipelines. And more recently, what we've been doing is trying to, instead of depending on service owners to come up with their own experiments, we're trying to automatically generate experiments and run them on a regular basis. So, for example, we'll use our monitoring system to introspect services and say, okay, what's like the 95th percentile latency? What is the timeout that your RPC client is set to? And then we'll inject latency, so that the 95th percentile is just very close to the timeout, but not quite there, and see whether your system can handle that. The last one is minimizing blast radius. So it is dangerous to run in production. You do need tooling to be able to protect yourself in case something bad happens. So what we do is we only affect a small amount of traffic when we do these experiments. And we have a bunch of sort of auto stop logic. So we're able to detect very quickly if some of our KPIs are going south for the experiment cluster, or if there's any difference at all between the two clusters. And if that happens, like within a minute, we'll just stop the experiment early. So if you don't take away anything from the talk, here are the takeaways that I hope you do. One is that our systems are going to behave pathologically, right? They're going to act in really weird ways that you would not have been able to predict in advance. But with chaos experiments, you can root out some of these pathologies. You can find some weird things in your system. The second takeaway is that one of the reasons we get into trouble is that people are making reasonable decisions based on the information they have and based on the constraints that they're working under and the incentives that they have. But you can use chaos to sort of push the incentives, in a more, sort of reliable direction in some cases. And the final takeaway is I really recommend reading these books. These are really great books. The first one is The Systems Bible by John Gall, which was originally called System Antics when it was published. The second one is Dekker's Drift into Failure. The third one is a little bit self-serving. That's a book written by my team at Netflix. However, while you have to pay money for the first two books, the third book is free, and we've got copies at the booth. So come see me at the booth at the break, and I'm happy to give out a copy of the book and answer any questions you have. Thank you.